Hi, everyone. Before, when we were discussing VAs, we assumed that this rational expression was simplified, that they had no common factors, certainly not common factors in X. Now, bear in mind that HAs and SAs, horizontal and slant asymptotes, don't care about whether the expression is simplified or not. For example, HAs just care about the leading terms. Now, how are these different? Well, VAs deal with sudden explosions, like in the middle of a graph. HAs and SAs both deal with long run behavior, like as X approaches infinity or negative infinity. So in that sense, they study very different things. Now, they do have a few things in common. What are the few things they have in common? Well, in common, they're lines, right? An asymptote is a line that a graph approaches, broadly speaking. In particular, we draw them as dashed lines, and they involve ideas of infinity. But beyond that, these actually have surprising little in common. VAs deal with sudden explosions in the middle of a graph. HAs and SAs deal with long-run behavior. And the way we obtain these is very different. And again, VAs care about whether this is simplified. HAs and SAs don't. Now, what if this is no longer simplified? What if n of x over d of x is no longer simplified? In particular, what if they have real zeros in common? Then it's possible that at such a common real zero, we could have a VA, or we could have a hole. This is something we haven't seen yet in this section, because if the given expression is simplified, you're not going to get holes. But if the given expression is not simplified, you could get a hole, where you have a real zero in common. All right, here's an example. Graph y equals, or f of x equals, x squared minus 9 all over x minus 3. You may be itching to do what to the numerator? How about factor it? Let's factor the numerator. And what do we get? We get x plus 3 as a factor times x minus 3 as a factor. And what can happen? These cancel out, they divide out to 1. By the way, something you may have observed that 3 is a real zero for both the numerator and the denominator. If you plug 3 in for x in the top and the bottom, you get 0 on the top and the bottom. So notice that 3 is a real zero of both the numerator and the denominator. So what do we have at x equals 3? At x equals 3, you know, before, when we had like 1 over x minus 3, we knew we had a what at x equals 3? We knew we had a VA. But here, since this is not simplified, it turns out that there could be a hole. So right now, at x equals 3, we can say that there will either be a VA, a vertical asymptote, or a hole. It's going to be one or the other. But which is it? Are we going to get a VA or a hole? All right. Bear in mind that if 3 had not made the denominator 0, then we would have had a point, a bona fide point. All right. So these cancel out, and we're left with x plus 3. But now, remember something we talked about early in the course. X cannot be what number? X still cannot be 3. If 3 was an illegal value for x back here, we have to make sure to remind ourselves that 3 is still illegal over here. We have a hidden restriction. Do not forget your hidden restrictions. All right. And if you have a hidden restriction like this, very often that leads to a hole. And in fact, here, it will lead to a hole. we're going to get a hole, not a VA. All right. Because if the restriction were obvious, it would be a VA after the simplification. If you need a hidden restriction, then you're probably getting a hole. All right, so what do we have here? I'm claiming that x squared minus 9 all over x minus 3 is equivalent to this expression, x plus 3 with the hidden restriction that x cannot be 3. So how would you graph y equals this fraction? Well, you would graph basically y equals x plus 3. How would you graph y equals x plus 3? It's a slanted line. Right? Here's our old friend, y equals x plus 3. It's a slanted line. And ordinarily, the point 36 would be on the graph if we had the line y equals x plus 3. But now, wait a minute. We're saying that x is not allowed to be 3. So actually, if you're going to graph y equals this original fraction here, we're not allowed to have a point with x coordinate 3. So technically, we're supposed to have a hole there. The graph of y equals x squared minus 9 all over x minus 3, it looks like this. It's the graph of y equals x plus 3, but since 3 is not in the domain of the function, we're not allowed to have a point with x coordinate 3. We have to pluck the point 3, 6 out of the graph, and we're left with a hole here. The official terminology in calculus is that we have a removable discontinuity at x equals 3. In the sense that it's easy to think of a related function where you fill in that hole. Personally, I think that's a bit of a misnomer. You don't have to write the fill in the hole because you feel like it. All right. But we have a removable discontinuity at x equals 3. We have a hole. It's a hole, not an open endpoint, because we have neighbors immediately to the left and neighbors immediately to the right. It's a hole. Now, by the way, you're smarter than Desmos. If you ask Desmos to graph y equals this, what happens? Y equals, parentheses, x squared minus 9 over, parentheses, x minus 3. Okay, I'm putting the parentheses to be safe. Now, wait a minute. You might be saying, well, hey, this just looks like the line y equals x plus 3. So Desmos might be tricking you here. But you know what? This is why you need a human operator. Desmos is not being honest with you. Desmos really should be clearly indicating a hole there. If Desmos gave me this for a homework answer, I would mark Desmos wrong. You hear that, Desmos? I would mark you wrong. Although, to give Desmos credit, if you try to click on the point where, if you try to click on the point where 3, 6 would have been on the graph, see here, at least when you click on the point 3, 6, Desmos does admit that the function value is undefined there. But you have to click on 3, 6 in order for Desmos to tell you that. If you don't do that, just by looking at this picture, you wouldn't know that there's supposed to be a hole at 3, 6. You have to actually click on the graph for Desmos to remind itself that there's supposed to be a hole there. Okay, so you're smarter than Desmos. Desmos should be putting a hole there, and it's not. Okay, so on homework, you should be doing something like this. Draw the line, but clearly indicate the hole here. All right, now why do we have a hole? Well, good question. Why do we have a hole? Why do we have a hole at x equals 3? Okay. First of all, why do we have a hole and not a point? Because 3 is not in the what of this function. 3 is not in the domain of the function, because x equals 3 would give us a 0 denominator. 3 is not in the domain of f, so we can't have a point on the graph with x coordinate 3. Okay, the 0.36 is not allowed to be on the green graph because 3 is not in the domain of the function. So we know we cannot have a point on the graph. Notice x cannot be 3. 3 is not in the domain. Now, algebraically, why do we have a hole? It's because the corresponding factor, x minus 3, gets completely canceled out. The factor, x minus 3, is completely canceled out or eliminated in the denominator. We started off with an x minus 3 factor down here, all right? But it gets completely canceled out by the x minus 3 factor up here. By the way, one consequence of the fact that 3 is a real 0 of both the top and the bottom, that means that x minus 3 must be a factor of both. So 3 is a real 0 of both the numerator and the denominator. One implication of that is that by the factor theorem, x minus 3 is a factor of both. So if you notice that 3 is a 0 of both the top and the bottom, that's a hint to help you factor. That means x minus 3 is a factor of both the top and the bottom. And that turns out to be true. That may help you factor this thing on top. Again, why do we have a hole? Because 3 is not in the domain of f, so we're not allowed to have a point on the graph there. And the corresponding factor x minus 3 is completely canceled out in the denominator. So here's the thing. Normally, if the denominator is approaching 0, we're in trouble. We might have a VA, or vertical asymptote situation, like a big sudden explosion. But because we have a twin, an x minus 3 factor up here, who ultimately destroys all the x minus 3 factors down here, the x minus 3 factor in the denominator is no longer a threat. It's like you're putting a robot over a bomb. The x minus 3 factor is no longer a threat. It's completely canceled for the denominator. And now, as x approaches 3, we don't have a problem of the denominator approaching 0 anymore. As x approaches 3, the denominator no longer approaches 0, and we're safe. All right. Now, if x minus 3 factors do survive, we'll have a VA. We'll discuss that issue later on. How can we tell we have a hole at the point 3 comma 6? Well, it's a limit problem. To find the limit of f of x as x approaches 3, you take the simplified expression and plug x equals 3 into here. So 3 comma 6 is the hole on the graph because when you plug in x equals 3 into the simplified expression, x plus 3, you end up with 3 plus 3, or 6. Remember, the limit value is the y-coordinate that you approach if you run towards this hole from the left and from the right. You're approaching a y-coordinate of 6, so it's the limit value. The function value at 3 doesn't exist, but the limit value exists. It's 6. So this function here approaches 6 from either the left or the right. If you acknowledge that there's a hole here, all right, then the y-coordinates approach 6. The function values still approach 6 from the left and from the right as x approaches 3. So to find the y-coordinate of the hole, you plug x equals 3 into the final simplified expression, and you get 6. That's the limit value. That's how you calculate that limit value in calculus. All right, so that's why we have a hole at 3 comma 6. Again, 3 is not in the domain of the function, so we're not allowed to have a point on the graph. That means we either have a hole or a VA. How do we know we have a hole and not a VA? Because the factor x minus 3 down in the denominator is completely canceled out. It's completely eliminated. So it's no longer a threat as x approaches 3. All right, next we'll talk about the VA case.